Is it working?
Hi.
Oh,
Hi, folks. Seems to be working. Now I'm going to try to explain a few things about two interestingly different subjects. I'm going to mix Spot and cost reduction on EKS, and I'm going to be talking about some custom silicon that we have developed that has also the interesting advantage of helping you reducing the cost on AWS. So, who am I? So I'm Arthur Petitpierre, a specialist solution architect at AWS. And I look more specifically at our A1 EC2 instances, who happen to be based on an ARM processor that is custom designed from AWS. I just moved to the US, and you might happen to see me one day carrying snowballs, which are one of our very few physical appliances on my cargo bike. So let's talk a little bit about the different purchase models that we have on AWS. So as you might know, there are mainly three different models when you want to use compute resources on EC2. The first model is the on-demand model. That's the simplest, that's the default one. Whenever you need an instance, you just launch it, use it for as long as you need it, and you pay by the second. That's the simplest and the most convenient, but that's also the most expensive. So as much as it might fit you for when you're just discovering AWS, as soon as you start to have a real intensive production utilization of AWS, you might be starting to look for alternatives. One of those alternatives to reduce the cost is to use reserved instances. Reserved instances can offer you up to slightly more than 60% discount, but they're not as flexible as the on-demand instances, because what you trade for a cost reduction is basically an engagement to use those instances. So you commit to use those instances for a year or up to 3 years, and in exchange for that commitment, AWS is going to give you a discount on those instances. But you commit to use them full time, and you are going to pay whether you use them full time or not. So that's a pretty good model for, let's say, any critical application that's going to be running 100% of the time. But for applications that are scaling up and down regularly with microservices, that may definitely not be the right model. You might use it as the basis to have a couple instances that are using it, but because you know you're going to use them all the time, but you cannot count on that to manage the flexibility that you need. Then comes the Spot model. The Spot model offers you a potentially way bigger cost reduction, up to 90%. The trade-off for that is that you're going to be using spare capacity that neither the reserved instances nor the on-demand instances are going to use. So you use instances from our spare pools, and we give you that huge discount, but the trade-off is that whenever we need those instances to serve the on-demand market, we are going to get those instances back within a short notice, within 2 minutes notice. So that's pretty good, but that's rather for fault-tolerant, flexible, and stateless workloads. Some of you might remember of the old Spot model. We used to have a Spot pricing model that was based on customer bidding for the price of the resources, and depending on the demand, the prices of the Spot instances would go up and down, potentially up to 10 times the price of the on-demand market, and down to 90% discount. We changed that model in November 2017. So now you no longer have to bid when you request a spot instance. What the possibility you have is to put a higher limit to the price you're going to pay for those instances, but no longer a bid price. So there's no longer any risk for a customer requesting a very large number of instances and outbidding you. You no longer have to figure out that complicated game of what's the best bid price depending on what I want to do. The only thing you have to figure out is how much I want to pay, because potentially the workload you're running is a workload you would only run if the spot price is at 50%, is lower than 50% of the on-demand price. Let's say, I don't know, you're resizing batches of images and you can afford to wait a little bit longer to do that. That could be an example. And so, yeah, we made that simpler for you. You just request the capacity and you pay the current rate. And the only interruption that might happen is when the on-demand market put pressure on the spot pools, and then we might claim instances from you. We have a pretty large number of customers leveraging the spot market in many different verticals. In the research verticals, like people doing genome sequencing, that's the kind of workloads that fits pretty well with managing interruptions. We have people in the ad tech market. We have people in the financial services market who are running the risk calculations on the spot market. Same thing, handles interruption pretty well. You launch thousands of compute tasks at the same time. Each of them is loosely coupled with the others, and you can afford to retry if one of them is on a spot instance that would be reclaimed. EC2 Spot is pretty well integrated with our services. A good example being Amazon EMR, where you can choose to have your worker nodes running on Spot. Typically, it will handle a Spot instance being terminated and rescheduling the job on a new instance. It's also integrated with AWS Batch, who will, same thing, handle rescheduling a job in case of a Spot failure. And it's also integrated with many of the third-party applications that can run on AWS, like Kubernetes, and we will talk about that in a minute. Is your workload spot ready? The first thing that is super important is if your workload is stateless, that's a super good candidate for Spot. If it's fault tolerant, because of the potential interruption, it's a good candidate for Spot. If you're flexible on the types of instances that you can use for your workload, that's also a good candidate. If it's loosely coupled, good candidate. Does it remind you of container-based microservices? That's exactly the reason. Sorry. Okay. There it goes. Illustration of the change in our pricing model. What you see on the left part of that graph is the evolution of the prices on one instance type in several availability zones before and after we changed the model. So the left part, you see that the price can go up and down pretty brutally, let's say, from 90% discount to a price that would be higher than the on-demand price. November 19th, 2017, we applied our new pricing model. And now what you get is a more predictable price that will only slowly fluctuate. The difference between the two is that On the first one, you would be interrupted because of the price changes. Now you will be interrupted because we manage the reclaim of the instances in random order among all the instances that are available in the pools. The EC2 Spot pools, those pools are a three-dimensional market, which means that you have a pool per instance type, per instance size in an instance family, per availability zone, and the price of those different pools is evolving independently. And it's evolving independently in all the different regions, which means that you can leverage that three-dimensional plus the region dimension to diversify your resources and leverage as much pools as possible in order to ensure that you always have a pool that will have resources and never end up with no resources at all. Using one of our dashboards, you can also measure the savings you're doing by using Spot. That example is taken from the dashboard of a Spot fleet that shows you the effect of diversifying that Spot fleet across several different instance types. And in that case, you get 70%, more than 70% discount. What about interruptions? What we observe is that more than 95% of the Spot instances are not interrupted by AWS over 3 months, which means that most of the Spot instances are interrupted upon customer demand and not by AWS. Anyway, the work you're doing to make your application fault tolerant, because hardware does fail, network does fail, code does fail, that work is also benefiting to Spot, because you will be handling the same kind of failures. Spot is there to allow you to do cost reductions for these stateless, fault-tolerant, or flexible workloads. One of the things you can do to handle those interruptions a little bit more smoothly is that you can handle the 2-minute termination either by looking at the metadata of your instances. There's a flag that gets raised 2 minutes before your instance is interrupted. The other solution being to listen to CloudWatch event, because you will be receiving through CloudWatch an event 2 minutes before your instance is going to terminate. And then you can handle this signal to take whatever appropriate method to handle the checkpointing of the application that might be running on those nodes. That could be rescheduling a pod in your EKS cluster to another instance, for example. Which is a good transition to how to leverage Spot for Kubernetes on Amazon, so on EKS. You can perfectly have a daemon set on every worker that would catch the Spot interruption and coordinate the shutdown of the node and the drain of the node. You can also use labels on your nodes to identify those who are running on the Spot market and only schedule on those pods the workloads that can afford to be interrupted. You can also leverage the possibility to diversify your resource groups, either directly through EKS or through our auto-scaling groups. And to make a summary of that, the main points that you have to put in place to be successful with Spot and take advantage of those cost reduction is first to be as much as possible instance agnostic and let either the auto-scaling group or the Spot fleets to provide the capacity at the lowest possible price. Use our launch templates to benefit from those new ASG and fleet features. The instance families that you will leverage will have an influence on the interruption rates. Not all the instance families are equal. Some of them do see more pressure, potentially some new generation instances might have a higher interruption rate. So if you can afford running on an older instance type, that might bring you additional benefits and lower prices. And of course, architect your application to be as much fault tolerance as possible to increase your availability. But that's a general rule. If you want to dig deeper, we do have a Spot instance workshop that is available. It also covers EKS. It's available on demand, and you can go through it yourself. It's made of small labs, each of them taking roughly 20 minutes to be run. You can definitely have a look. Next thing, you all probably know that we have instances leveraging AMD and Intel processors. Who's aware that we also do have instances with our custom ARM-based processor? Quite a few. Thank you. So we released last year at reInvent the first generation of instances that do have a processor designed by AWS. Those Graviton-based instances do have the latest generation of our custom silicon. And our A1 instances were designed for scale-out workloads and offer up to 45% cost savings compared to M5 instances, for example. Those have a 64-bit ARM-based processor, and they use the same hypervisor as our other instances, the Nitro hypervisor, that brings you a really low level of jitter and maximize the performances. The target applications for our A1 instances are the web tier of an application, containerized microservices, caching fleets, IoT, gaming, and potentially other ARM-specific workloads like dev and test for embedded applications. The software ecosystem for our ARM-based instances, for our A1 instances, is pretty extensive now. We have, of course, support for Amazon Linux. We also have support for Ubuntu, SUSE, Docker Desktop, and Docker Enterprise do support the ARM target. And since we launched, many other distributions have added support for our ARM instances. As far as containers are concerned, Amazon ECS is available today and can take advantage of A1 instances. And EKS is available as a preview. And I'm going to give you the link later to the preview. And as far as the tools are concerned, most of our management tools are available. And if your application do leverage Java, we even have Amazon Corretto, our open source long-term support version of Java, supported by AWS, is available on A1. Here's the link about the EKS preview. If you have any question about it, please feel free to send me an email. My email address will be available at the end of the presentation. And we had just yesterday a blog post from one of our heroes, Casey Lee, that has been published and that covers cost optimization for Kubernetes on AWS. Now, let's switch to the demo part. The goal for my demo is going to be to show you how to generate containers for both x86 and ARM64 at the same time, and use those containers for a super simple web application that I'm going to launch. We are going to leverage Docker buildx, AWS CloudFormation, a load balancer, and a few instances, both x86 and ARM64. The architecture of the demo could not be simpler. That's just an ALB in front of two instances, and I'm going to launch a x86 64-based containers on the T3 instance and an ARM64 container on the A1 instance. So let's look at the code. So here's the super simple, probably the most simple web application I could have coded. So it's a small piece of Go that just bind on the port 8080. And when handling a request, is going to answer, "Hi, container day folks, I'm running on this or that type of architecture." So we are going to log on an instance and run the build. So let me quickly log into my EC2 instance. So I have an instance that I pre-configured with Docker and all the tools that I needed for that. So here it is. Am I logged? Yes. So that instance is an x86-based instance. That's I think I took a C5 2XL. And on that instance, I installed a beta version of Docker so that I can leverage buildx. The first thing I'm going to do is I'm going to create a new builder. So let's first so I printed all the instructions that I'm going to run. The first thing is I'm going to make the list of the different builders that I have available. So I only have the default builder. So I'm going to create a new one. That I'm going to call demo builder. Super original. I'm going to tell Docker to use it as my default builder and bootstrap it. So I installed everything that was needed to be able to build a ARM64 container. And now I'm going to build a container that's going to contain the small application that I just shown you. So the Docker file for that application is going to be the following. I'm going to use a small Golang Alpine container as the builder, and then push the Go binary that I will generate into an Alpine, a minimal Alpine container, and then use that container to expose my application on port 8080. So let's go back to the builder container, and let's generate my container. So I'm going to change the version of that. Let's say version 9, because I built a few in between. And let's launch the build. So what the builder is going to do, since I told him to generate the container for the Linux x86 platform and the ARM64 platform, is that it's going to run both builds at the same time, and it's going to push the same container for the two different architectures to Docker Hub. While it's building, it's going to take a little bit more than a minute to be built. Let's have a quick look at what we are going to do to deploy that application. So I've wrote a small CloudFormation template, pretty simple, just one parameter, which is going to be the container that I pushed to Docker Hub, a ARM64 instance that is pretty simple. The only thing that I do here is that I have a script that is going to install Docker and launch my container. Exactly the same thing for an x86 instance. And then I'm going to put in front of that an ALB with a target group that contains both instances, so my ARM64 instance and my AMD64 instance. So now my container should be built. So that's OK. It has been pushed as the v9 of my container. And we can switch to the next part, which is going to be deploying that thing. So let's switch back to CloudFormation. Here we are. So I already deployed a backup stack with exactly the same application, but we are going to deploy a new version of it. So let's take my template, choose my template file. So that's the one I just shown you. Let it being validated. It does not answer. Let me reload that page. What's happening? Okay. Let's relaunch the creation. Now it's validated. Next step, give it a name. Let's call it demo stack. We will update the container version to version 9, which is the version we just generated. There's nothing to change in that stack. And now let's push it to deployment. So the stack is going to start. It's going to start the deployment of the two instances, my elastic load balancer. And in a few minutes, usually it takes up to 2 minutes to deploy, it's going to complete. In the meantime, let's look at the one that was already deployed. So it has deployed an AMD64 instance. It has deployed an ARM64 instance. And in front of that, we have the ALB. So let's look at the output, because the output is going to give us the DNS address of that ALB. And let's have a look at whether the application answers. Yeah, so that one is running. So the ALB has done its load balancing work, and we ended up on an AMD64 instance. So now I've written a little script that's going to launch 100 of requests in a row to the ALB, so that we will check that the requests are indeed launched on one or the other instance type. So the script is there. Let's launch the test, and it takes as an argument the DNS name of the ALB. So let's give it the DNS name of the ALB and go. And now we see one after another, one time an ARM64 bit and the other time an AMD64. So what have we seen? We can take exactly the same code and with a super minor work, generate a container that would match both an x86 and an ARM64 instance. Those B-arch containers are pretty easy to build thanks to the work done by Docker. And our AWS EC2 A1 instances are yet another lever that you can use to reduce your costs. Thank you.